So welcome everyone. My name is Bhagat. This is Steffen and Kishan from Google. We are here to talk about how we bring pins into an SDN world and the challenges we faced and some of the solutions. I wanted to discuss them with you. So last year at OCP, we introduced the pins stack. It's an addition on top of SONiC framework and allows SONiC to work with a remote SDN controller. We introduced P4 runtime, an application, and then P4 Arc, an Arc agent in Swiss container. Since then, we have been working on pins to make this a robust and reliable and highly performant stack. And today we'll talk about some of the challenges we faced and how we solved them and etc. We'll go through a brief overview of SDN, configuration, event handling, and a bit about performance. And Kishan will talk about some of the features, dynamic port breakout and in-band. We'll also talk about the challenge of saving intent in an SDN switch. And then Steffen will take it on from there, look at it from a controller perspective, and talk about sequencing of programming, and also about how a controller can effectively manage resources that are spread across the different switches in its control, and how to deal with resource exhaustion. So in SDN kind of a network, the controller knows about the network topology. This is generally, a controller is generally done in a single domain and where there is full knowledge about the domain, and there is a single administrator taking care of it. So it's in charge of configuring and operating the network. It also handles any notifications from the network. So all of the switches that are under the control of a controller send it events. They have a dedicated channel to the controller and send it events. The controller listens to all of those events and figures out what needs to be done in response to an event, and then handles those notifications. Let's take an example of a switch down scenario. So when a switch goes down, it may or may not be able to send an explicit signal that it's going down. However, neighboring switches will detect that the links are going down, and those will be sent in events to the controller. And the controller also realizes that its own channel to the failing switch is down now. So using these information, the controller will be able to deduce that the switch is down and take appropriate action. So whether the notification is implicit or explicit, the controller needs to take it into account and then figure out what to do to make sure that the network remains robust and is switching packets continuously. Moving on, let's talk about configuration workflow. As the configuration is sent from the controller to the switch, in the pin stack in SONiC, for example, we have a gNMI front end which receives the requests, parses it, verifies it, and writes it to config.db and sends a pass response back to the gNMI client. Now, what has happened is the controller sent a request and it has received a pass response, but the configuration has not really reached the hardware. And this is due to the layered architecture we have in SONiC. It's an eventual consistency model. So how do we get a confirmation of completion? So we get that by the backend in the switch. It picks up the configuration and writes to the hardware. The state gets reflected in the database. The controller has to now subscribe to state information that is in the database so that it can pick up this new information that the config has eventually reached the hardware. And this is part of the workflow that happens in the switch. And this is something that the controller needs to not just send the configuration and wait for the response, but also asynchronously it'll receive these responses that the state has eventually merged, and it needs to learn from that. And as we worked in SONiC, we found that there are certain config knobs and certain state information that we had to add to make an SDN network work effectively. And we have added those. Let's take a look at an example of a Dataplane event workflow. As I mentioned, the controller subscribes to a lot of events. And this is not just configuration events, but also asynchronous events where, for example, a link goes up or down. The controller would like to know and take immediate action. And in these cases, the backend notices that there is a change, and it reports it through gNMI telemetry. The controller takes this and computes the changes and sends new requests. And these new requests now could go to the failing switch or could go to the neighboring switches. And all of these switches get programmed. These are things that happen in an SDN controller world. Let's take one more example of something that happens in this kind of a world. In traditional switches, if there is a failure, the switch logs the failure, attempts to correct it, and if it cannot correct it, it tries to do things like process restart, system restart to correct that problem. In an SDN world, the same first step happens. The switch logs and attempts to correct it. But if correction fails, rather than do process or system restarts, which may disrupt the network, it raises a flag and says, I'm at a critical state now, and sends this communication to the controller. The controller can then take corrective action of rerouting traffic around the switch and then restarting the switch. So this ensures that data plane traffic that was already flowing continues to flow until all the traffic is removed from that switch and the switch is repaired. So these three examples are different scenarios that can happen in an SDN world, and how the controller, in coordination with all the switches that it controls, can work together to ensure a robust and reliable network. And as you notice here, the reaction time from the controller is extremely critical. The notification time of an event, the switch detecting it and sending it up, the computation that happens in the controller, the communication back of what change to be made, and then the programming in the switch and a confirmation. All of these is what we can call as a reaction time, an end-to-end reaction time, to get the network back up and running. And there are scenarios like WCMP pruning where a local speedup can happen. In cases where, let's say, there is a WCMP group and one of the member links goes down, the switch can correctly deduce that the controller is going to ask it to remove that link from the group. So it can take an action before going through a notification, computation, communication loop. And there are places where you can do local speedups. But this is not possible in all scenarios. So end-to-end performance of reaction time is an important criteria for SDN networks. And here's where we get a bunch of challenges. We have a layered architecture in SONiC. It's great for modularity, but it's also challenging for performance. And as I mentioned before, we have a few missing knobs and state information. Right? So this also is important. We have been working on this one, and we are planning to upstream most of the additional config knobs that we have added and state information that we added. In fact, today morning in the SONiC community meeting, we talked about link damping. And this is a feature where we would try to reduce the amount of link flaps that we get communicated to the controller and back, and how reducing that communication, in fact, increases the performance overall. We also encountered the problem of slow notification path in the switch, and we have done a lot of performance improvements on that. And lastly, the hierarchical CRUD API in SAI and SONiC is also a cause for slowdown, and that's some place where we have done some changes. So to summarize, some of the changes that we have done in performance and optimization of this end-to-end reaction time is on bulk routing, passing multiple objects to SAI as a bulk and getting a confirmation. This is very good in terms of reducing the amount of IPC that happens between layers. Batch messaging, here it's not about a single object, but across different SAI objects, bringing them together and passing back and forth. And we also reduced the amount of Redis transaction that happened. We took an example of the ASIC DB synchronous mode where messages are passed through notification, and we actually brought it to the application layer between P4 runtime and Swiss, and we noticed a significant boost in performance. So these and a couple of other areas where we have focused and brought in a lot of performance, we are working on with the SONiC community to upstream these changes so that everybody gets the benefits of performance and being able to manage a SONiC switch through SDN controller or otherwise, right? From here, Kishan is going to talk about a few features. Where do we want?
Hello, mic check. Hey, good afternoon. So I'm going to cover probably 3 use cases or features where we kind of had some challenges in implementing them on SONiC and how we overcome them. So the first one is dynamic port breakout. So here, breakout essentially kind of breaks down the port like from one set of its channelized config to another set of channelized config, say 2x400 to 8x100 or something like that. So in order to do that, there are 2 entities kind of giving directions to the switch, right? Like one on the left side, you see gNMI where the config for the breakout comes. And then on the other side, you have the flows that can get programmed on these channelized ports, which are effectively getting broken out, right? So there can be coordination between the directions that come to these 2 entities, but intentionally we don't want to have those interdependencies too much, and it can happen that the configs can come independent of each other. So if a breakout config comes and what if there are flows that are referencing those referenced breakout ports, right? So then you can't allow that config to go through. So we had to do some additional changes on the gNMI front end to kind of monitor whether there are flows referencing the ports, right? So the reference count comes very handy in this case. So we kind of leverage that, and we kind of check whether there are any flows referencing, and then the gNMI front end can either accept the config or it can reject the config, saying that there are flows referencing those ports. Even with this solution, there can be kind of some corner cases where the front end found that the config can go through and it allowed the config to be written to the config DB, but finally in a short span of time before the backend could take that and break out the ports, there could be some flows, some new flows that are kind of that have started referencing the port, right? So in those cases, what happens is that we again kind of rely on this eventual consistency model. So if this happens, the backend is not going to go ahead with the processing of the breakout config, and that will eventually get reflected in the state DB, right? Because the state DB is going to be updated only when the breakout config succeeds. So the controller is going to keep monitoring the state DB to see whether the breakout happened or not, and after a while it's going to find out that it's going to time out, and then it will kind of take a drastic action, or it will try to mitigate it by like kind of maybe deleting the flows referencing the ports, or as a worst case scenario even try to reboot the switch to recover from that situation. The next we look at in-band connectivity. In-band connectivity is essentially providing connectivity to the switch by means of the Dataplane ports. We are not going to use the out-of-band management like the management Ethernet or of anything of that sort, but rather we are going to connect to the switch via the in-band path. So we have a new container and a new process called in-band manager, which is going to take care of this establishing the connectivity. It's going to program some flows to enable that connectivity and all that. So again, there are 2 entities which come into the picture again here, right? So one is the switch, the process, the in-band manager that is residing on the switch, which is trying to program some flows. And then there is this controller intent, which is trying to program some flows, and it is trying to set up some path for other data plane purposes. So although we would like to not have an intersection between these two, we strive to do that, but sometimes it doesn't happen, and there is a conflict or there is a dependency between the flows that the controller wants to program and what the local in-band manager wants to program. So the way we resolve this is to basically have the in-band manager listen on some of the app-DB updates that happen that the controller programs, right. So it kind of listens to these updates and then takes some reactive actions to kind of mitigate the conflicts and then make sure that the path can be programmed in an effective way, right. So this is one place where we felt the challenge, and we kind of mitigated by having the in-band manager listen to the updates that happen from the controller side. The last is essentially the persistent intent config. So this is one use case where we see a more usage from even other teams that have kind of a need without the controller coming into the picture. So essentially the concept here is simple. The config DB is kind of resides on the Redis DB. We know that it is on the local RAM, so it is not persistent. But when the switch goes through an either a planned reboot or an unplanned reboot, we have to kind of come back as quickly as possible, and we also want to come back with the switch in a configured state as quickly as possible. So what we did is to move every time a config gets pushed, the gNMI will also persist that config into a persistent memory, and this persistent config is then restored during restart scenarios. So we had multiple challenges like learning non-default values and also the incremental versus the full file write, and we kind of have addressed some of these, and it will be reflective in the upstream that we plan to do. With that, I pass on to Steffen to go over the next sections.
Okay, so before I wrap up, I want to tell you about two challenges that we faced at the intersection, or rather the interface between the switch and the SDN controller. And let's warm up with a simple one that shows up in the area of what we call sequencing. So as you may know, SI objects form sort of a hierarchy of objects where some objects may refer to other objects, which in turn may refer to yet other objects. And so when you insert such an object, you need to respect this dependency graph, or DAG, directed acyclic graph, right? In the sense that you want to insert referee, so objects that are being referred to before the objects that refer to them, right? And so there's a question here. Who's responsible for this? Is it the switch or the controller? And initially, we opted for simplicity for doing this on the controller side. This makes the switch stack a bit simpler. And so that meant that in that model, when the controller wanted to set up a route, for example, it might need up to 5 round trips with the switch, because it would have to start by installing things like router interfaces and neighbors, next hops. Eventually, you would be able to build up a group, and finally program the route. More recently, we decided to move all this into the switch, which means that now for the controller to set up a route, it can just send a single batch with all of these dependent objects. And the switch will then take care of sequencing and breaking things up into step-by-step insertions. And similarly, in reverse order for deletes. So this improves performance, less network overhead. It's also a simpler API for the controller. So let's look at a bit more difficult one around resource exhaustion. So we really love that SI hides functional differences between various ASICs, right? This is where it really shines. This allows us to run the same switch stack across many different ASICs. However, as great as it is at hiding these functional differences, it really doesn't help us with hiding other differences, such as resource limits, right? So different ASICs have fundamentally different resource guarantees and limits. For example, the number of group members you can install on an ASIC depends on the ASIC, and that's not hidden by SI. And this turns out to be something that the controller really cares about. To understand why, recall that an SDN controller is essentially solving an optimization problem, right, where it tries to distribute traffic as efficiently as possible on the different paths that the traffic might take through the network. And so this is a constrained optimization problem, and some of the key constraints in that problem are how many members, for example, can I install on that switch? You have to take that into account. And so we really want to know that ahead of time. When we solve the problem, we don't want to learn at runtime that something the controller tried to do isn't possible. And so we need these static resource models for all our switches. So how do we address this? There's sort of a twofold approach here. So one is we basically have a simplified model for each of our switches that says things like how many table entries at a minimum this switch is going to allow in a certain table. And so these resource guarantees, they're programmed in the P4 program, and they're exported to the controller. And so this really serves as a contract between the switch and the controller. And so the controller is going to assume this contract, and the switch must uphold that contract. And contract is only really useful if you have some way to enforcing it. So how do we do that? We have two ways here. So on one side, since we do SDN at Google, we can go back in time and see all the states of our network in the past. And so we can replay all network states on our devices and make sure that they are supported. Another thing we do is we randomly generate table entries up to the limits that were promised by the switch. And that way we ensure that these will be supported in production. OK, so wrapping up. So we've open sourced pins. You've heard about some of these challenges that we've already solved, but there's a lot more challenges. And we really appreciate your input here and your ideas. So we encourage you to join our working group where we discuss designs, problems, and next steps. Join our Google group. And yeah, please help us bring SDN to SONiC. Thank you.
Great. Thank you so much, I think, for sharing your valuable insights. Any questions? I think we already are above time. But in case you guys have any questions, you can come in the center. There are 2 mics and can ask.
Very quick one. Thank you for the great presentation. Data modeling question. So you're clearly extracting a number of objects that are not covered by existing YAML models. And being Google, you're using properly open config northbound, while YAML layer in SONiC using very different schemas, model after radius DB. So are you doing some kind of data normalization in gNMI client? I mean, how do you provide end-to-end data instruction?
The question is about data normalization in gNMI client.
Yeah.
Sorry.
So you've got a set of SONiC YAML models that are not really working with open config models.
I see. So today, our gNMI focuses using OpenConfig as the YANG model. And we are working with, we want to make sure that the configuration that we send on these switches can also be used on any other switch, irrespective of the NOS. So we're mostly concentrated on OpenConfig.
So gNMI southbound will normalize data with existing SONiC YAML layer.
That is right. gNMI southbound will be working with respect to the SONiC database.
Thank you.
Yes.
Great.
Nicely on the slides, you show that you have a controller that is a cloud. But now also you mentioned that you manage multiple aspects of the network, multiple aspects on the configuration, and then also you have P4 runtime for installing flows. So who's responsible for enforcing isolation? As here you have probably multiple, applications running on top of your controller. And I can imagine a scenario when two applications install conflicting flows or conflicting config. So in terms of enforcing that isolation or correctness, is it something that you deal on the switch side or on the controller side?
Well, that's a great question. So in general, all of the things that we talked about is for generic controllers even, so where a controller, if it is interfacing with a bunch of switches, how does it do that? And as we worked on these interfaces, we started with gNOI, gNMI, and P4 runtime as the main interfaces of the switch. And we realized that we also need a GNSI interface, so that is some work that is going on in security on GNSI. Well, I'll add a pointer to the GNSI section in the link and in the presentations as it is published, and we can have continued discussions on that.
Sure. I think, thank you. For the sake of time, I think we can take it in the open space hours.